Okay, in this video we'll look at exercise number 13. 13, we should always try to cancel, if we can, factor and cancel numerator and denominator. The numerator cannot be factored, but the denominator has two values of x that will make it 0. So those will produce vertical asymptotes at x equals plus or minus 1, and those will be things that we'll have to pay attention to as we go through the process here. So we're starting with f of x is x squared plus 1 over x squared minus 1. And our first derivative then is, using the quotient rule, low d high minus high d low over low squared. Low squared. We'll multiply out the numerator and get 2x to the third minus 2x. Then another, but this time minus 2x to the third, and another minus 2x, all over x squared minus 1 to the second. Simplifying, we have a zero pair, 2x cubed and negative 2x cubed, and we end up with 4x over x squared minus 1 to the second power, and that's our first derivative. For the second derivative, we'll also use the quotient rule. We'll have low x squared minus 1 squared d high negative 4 minus high negative 4x d low. Now the derivative of the denominator, that is a function composition. Outside function is something squared. So we'll bring down the 2, leave the inside alone, reduce the exponent, and multiply by the derivative of the inside, and then we're done. And that will all be over the denominator squared, which is now x squared minus 1 to the fourth power. So we'll multiply out. In the numerator, we're going to have to expand. We'll lead with the negative 4, then expand. X squared minus 1 to the second power would be x to the fourth minus 2x squared plus 1. Then minus negative 4x is plus 4x times. We have 2x times 2, which is 4x, times x squared, which is 4x to the third power. Then 4x times negative 1 is 4x. Again, all over x squared minus 1 to the fourth power. Multiplying out, negative 4x to the fourth plus 8x squared minus 4 plus 4x to the fourth power minus 16x squared over x squared minus 1 to the fourth. Now we can combine. Sorry, above we should have 16x to the fourth power. And since we had 4x times 4x to the third power, the algebra, the multiplication, the arithmetic is so critical in all of this. It really requires painstaking accuracy. So we have 12x to the fourth power, then minus 8x squared and minus 4 over x squared minus 1 to the fourth power. Factor out of 4, and that leaves 3x to the fourth power minus 2x squared minus 1 over x squared minus 1 to the fourth power. Now, fortunately, this is not too difficult to factor, since we have 3x as is a prime number, and the last number is a 1, so it has to be set up this way, and we need a negative 2x squared in the middle, so we'll have minus 3x squared plus 1x squared, and that is going to do it. One final change that we can make is that we can cancel an x squared minus 1 with one of the x squared minus 1's in the denominator and end up with 4 times 3x squared plus 1 over x squared minus 1 to the third power, and that is our second derivative with a lot of work. Now the next thing that we want to do is to set up our number line. Now we have to find potential points of inflection. A rational function is 0 where its numerator is 0, but our numerator will never be equal to 0. And the denominator has only the vertical asymptotes that we spoke of before. And so that would be at negative 1 and at positive 1, and we're working with the second derivative here. So we need to test values to the left of negative 1, between negative 1 and 1, and to the right. If you look at the numerator in our second derivative, it will always be positive, no matter what we put in for x. So the numerator is always positive. However, the denominator can be negative, since there's a minus sign inside and there's a third power on the outside, an odd power. Plugging in negative 2, we'll get positive. Plugging in 0, we'll get negative, and plugging in 2, we get positive. So concave up on the interval from negative 2, sorry, that's not negative 2, negative infinity to negative 1, and then again from 1 to positive infinity, and concave down from negative 1 to positive 1. Now it's important to note that even though we have two places where the concavity changes from first from positive to negative and second from negative to positive, because those occur at vertical asymptotes, there will be no points of inflection in this case. So no points of inflection. Because the places where the concavity changes are not points on the graph. They're not values in the domain of the original function. And you could graph this on your graphing calculator and you would be able to see that we have exactly what we're told here. Concave up, left of negative 1, then concave down between negative 1 and 1, concave up again after positive 1. And that'll do it for this video and this problem.